You've never seen an atom, neither have I. So why do I act like they're real? Explain it to me. Because here's the thing that drives me crazy. People treat atoms exist like it's a belief system, like it's a model we choose to use because it's convenient. Like tomorrow we might wake up and decide, never mind. Different model now. That's not what's happening. Atoms aren't a metaphor. They're not a teaching tool. They're not a placeholder for whatever the real thing is. They're the real thing. And I can prove it to you in about 10 minutes using nothing but stuff you've already seen with your own eyes. Let me show you what I mean. Imagine you're looking at a glass of water under a microscope. Not a crazy high-powered one. Just a decent optical microscope from a high school lab. You drop a tiny grain of pollen into the water. And you watch. The pollen grain doesn't sit still. It jitters. It dances around like it's being smacked from every direction by invisible fists. This is called Brownian motion. And here's the kicker. Nobody told the pollen to do that. There's no current in the water, no vibration in the table. The pollen is just bouncing. Why? Because water molecules' atoms are slamming into it. Constantly. From every side. Trillions of collisions per second. You can't see the water molecules, but you can see their effect on the pollen grain, clear as day. And here's what makes this evidence devastating. The math works. If you assume water is made of tiny particles in constant random motion, you can predict exactly how that pollen grain will move. You can calculate the average distance it'll travel, the pattern of its jitter, the relationship between temperature and motion. And when you measure it, the numbers match. Not approximately, not close enough. They match. That's not a coincidence. That's atoms. Now let me hit you with something even simpler. You walk into a room. Someone's baking cookies in the kitchen. You smell them. How? Did the oven reach out and poke you in the nose? Did the cookies teleport scent particles directly into your face? No. Molecules from the cookies are flying through the air, bouncing off other air molecules, spreading outward in a chaotic, random walk until some of them crash into the receptors in your nose. That's diffusion. And again, if you assume air is made of atoms and molecules in constant motion, you can predict how fast a smell will spread, how temperature affects it, how pressure changes it. You can calculate it, and when you measure it, it works. Every single time. You can't explain diffusion without atoms. You can't explain why hot air spreads smell faster without atoms moving faster at higher temperatures. You can't explain why perfume doesn't just instantly fill a room without the random chaotic collisions of particles. The evidence is everywhere. But let's go deeper. Take a chunk of salt. Sodium chloride. You can see it's made of little cubes. Perfect, sharp-edged cubes. Why cubes? Because sodium and chlorine atoms stack in a specific geometric pattern, a repeating grid, a crystal lattice. And here's the beautiful part. If you know the pattern, you can predict everything about the salt, how it breaks, how it dissolves, how it interacts with light. You can even predict the exact angles of those cube faces, and when you measure it, the angles match the prediction. Now look at graphite. Carbon atoms. Graphite is soft, slippery. You use it to write on paper. Diamond. Also carbon atoms, but diamond is the hardest natural substance on Earth. Same atoms. Different arrangement. In graphite, the carbon atoms are arranged in flat sheets that slide over each other like a deck of cards. In diamond, every carbon atom is locked into a rigid three-dimensional cage. That's it. That's the only difference. And because of that difference, graphite makes pencils and diamond cuts through steel. You can't explain that without atoms. You can't explain why the same element behaves completely differently without understanding atomic structure. The arrangement matters. The bonds matter. The geometry matters. And all of it, comes from the fact that matter is made of discrete particles that connect in specific ways. Now here's where people get confused. They say, okay, but you've never seen an atom, so it's still just a theory. And that's when I lose my patience. You've never seen wind. You've seen leaves move. You felt air on your skin. But you've never looked at wind and said, ah, yes, there it is, the wind itself. You infer wind from its effects. Same with gravity. You've never seen gravity. You've seen things fall. You've felt weight. But gravity itself, invisible. Same with magnetic fields. Same with every fundamental thing in physics. We don't see the thing. We see what the thing does. And atoms, we see what they do everywhere. But fine, you want to see an atom? Let's talk about electron microscopes, not the optical kind, the kind that use electrons instead of light. Why electrons? Because electrons have a much shorter wavelength than visible light. And the smaller the wavelength, the smaller the thing you can resolve. With an electron microscope, you can map the surface of a material down to the atomic scale. You're not taking a photograph, you're measuring interactions. You're detecting where electrons scatter, where they bounce, where they get absorbed. And when you compile all that data, you get an image of individual atoms arranged in rows. Or take a scanning tunneling microscope. STM. It drags a needle so sharp that the tip is literally 1 atom wide across the surface. And it measures the quantum tunneling current between the tip and the surface. When the tip is over an atom, the current spikes. When it's over empty space, the current drops. You scan back and forth, row by row, and you build up a map. And what do you see? Atoms, arranged in grids, in lattices, in perfect repeating patterns. You can even move them, one at a time. Scientists have used STMs to spell out words by dragging individual atoms into position. That's not a model. That's not a metaphor. That's control. But here's the thing that really gets me. People act like this is some esoteric, high-tech thing that only matters in labs. It's not. The fact that atoms exist is baked into everything you do. When you charge your phone, you're moving electrons, particles through a conductor. When you taste salt, sodium and chlorine ions are hitting receptors on your tongue. When you breathe, oxygen molecules are slamming into hemoglobin in your blood and sticking. Every single process in your body, in your car, in your computer atoms. And here's the scale that breaks people's brains. A grain of sand, tiny, right? How many atoms in a grain of sand? Roughly 10 quintillion. That's 10 with 18 zeros. If you counted 1 atom per second, it would take you 300 million years to count them all. And that's just 1 grain of sand. Your body, about 7 octillion atoms. The air in this room. Billions of trillions. And every single one of those atoms is doing exactly what the physics says it should do. Vibrating, colliding, bonding, breaking apart. All of it predictable. All of it measurable. All of it consistent with the same rules we've tested a million different ways. That's not belief. That's not convenience. That's reality. So here's the punchline. Atoms aren't something we discovered in the sense that we found a thing hiding under a rock. We discovered atoms by realizing that nothing else makes sense. Brownian motion doesn't make sense without them. Diffusion doesn't make sense without them. Crystal structure doesn't make sense without them. Chemistry doesn't make sense without them. Biology doesn't make sense without them. Every single branch of science independently points to the same conclusion. Matter is made of discrete particles. Those particles have specific properties. And when you know those properties, you can predict how matter behaves. That's what atoms exist means. It doesn't mean we have all the answers. It doesn't mean we understand everything about quantum mechanics or particle physics or whatever comes next. It means that at the scale of chemistry, biology, materials atoms are real. And the next time someone tells you atoms are just a model, ask them this. If atoms are just a model, why does every prediction work? Why can we engineer computer chips atom by atom? Why can we design drugs that bind to specific molecules? Why can we predict the exact structure of a crystal before we grow it? Models are useful approximations. Atoms are the thing we're approximations. Atoms are the thing we're approximating everything else with. That's the difference. You don't have to take my word for it. You just have to look at the evidence. And once you see it, really see it, you can't unsee it. The world stops being a smooth, continuous blob and starts being what it actually is, a storm of particles, colliding and connecting in patterns so precise you can calculate them. That's not magic, that's physics, and it's happening right now, in your lungs, in your screen, in the air between us. Atoms aren't something you believe in, they're something you reckon with. And here's what really gets under my skin about the atoms are just a model crowd. They don't apply that logic anywhere else in their lives. You trust your car's brakes, right? Those brakes work because of friction. Friction happens because atoms on the brake pad interact with atoms on the rotor. The engineers who designed your brakes calculated those interactions. They predicted the wear patterns, the heat distribution, the stopping distance, and it works. Every time you hit the brakes, you're betting your life on atomic theory. But sure, it's just a model. Your phone battery? Lithium ions, atoms moving between layers of material. The engineers know exactly how many ions fit in each layer. They know how fast they move. They know what voltage is needed to push them back and forth. That's why your battery has a specific capacity, a specific charge time, a specific degradation curve. All of it predicted, all of it measured, all of it controlled, at the atomic level. Or take medicine. You swallow an aspirin. It goes to your stomach, dissolves. The molecules enter your bloodstream, travel to sites of inflammation, and block a specific enzyme called COX. How do we know it blocks COX? Because we've mapped the shape of the COX enzyme down to the positions of individual atoms. We've mapped the shape of the aspirin molecule the same way, and we can see, literally see, with X-ray crystallography, how the aspirin molecule fits into the enzyme's active site like a key in a lock. That's not guessing. That's not philosophy. That's engineering at the atomic scale. And here's the thing that makes this even more absurd. We don't just observe atoms anymore. We build with them. There's a whole field called nanotechnology where people construct devices atom by atom. Molecular machines, quantum dots, carbon nanotubes. You can't build something out of parts that don't exist. You can't engineer with ghosts. Let me give you a specific example that'll blow your mind. Scientists have built a molecular motor, an actual motor made of a single molecule. It's about a nanometer across. That's roughly 10 atoms wide. When you shine light on it, it rotates, predictably, controllably. You can attach it to other molecules and use it to do work, to move things, to apply force. And the reason it works is because we understand exactly how the atoms in that molecule are arranged, which bonds flex, which electrons absorb photons, how the geometry changes when energy is added. Every detail predicted, every behavior calculated. That's not a model you're choosing to believe. That's a machine you can operate. Now let's talk about something that bothers me even more. People love to say science changes all the time. What we think is true today will be wrong tomorrow. And there's a grain of truth in that. Science does update. We do refine our understanding. But here's what doesn't change. Atoms exist. 100 years ago, we didn't know about quarks. We didn't know about the Higgs boson. We didn't understand quantum field theory. But we knew atoms existed. And that knowledge hasn't been overturned. It's been deepened. We've learned that atoms are made of smaller parts. Protons, neutrons, electrons. We've learned that those are made of even smaller parts. Quarks and leptons. But none of that makes atoms less real. It's like zooming in on a brick wall and discovering the bricks are made of clay. The clay is made of minerals. The minerals are made of crystals. At every level, you're discovering more structure, not less reality. Atoms aren't going away. They're a permanent feature of how the universe works. And here's why that matters. Understanding atoms doesn't just explain the world. It gives you power over the world. Every technology invented in the last century comes from understanding matter at the atomic level. Transistors, atomic physics, semiconductors, doping, band gaps, plastics, chemistry, polymer chains, molecular bonds, fertilizer, the Haber process, nitrogen molecules torn apart and reassembled into ammonia. All of it, depends on knowing that matter is made of atoms and knowing how those atoms behave. If atoms were just a convenient fiction, none of this would work. But it does work, and it works with precision. Let me hit you with one more piece of evidence that I think is underrated. Spectroscopy. You take an element, let's say hydrogen, and you heat it up until it glows. Then you pass that light through a prism. What do you see? Not a continuous rainbow. You see specific lines, specific colors at specific wavelengths. Hydrogen always produces the same pattern. Always. Helium produces a different pattern. Sodium produces a different pattern. Every element has its own unique fingerprint. Why? Because electrons and atoms can only exist at specific energy levels. When an electron jumps from one level to another, it emits light at a specific wavelength. And those wavelengths match exactly what quantum mechanics predicts based on the structure of the atom. This is how we know what stars are made of. We don't need to go to a star and scoop up a sample. We just look at the light it emits. We see the spectral lines. And we say, that's hydrogen, that's helium, that's iron. And we're right. We've tested this in labs. We know it works. And it works because atoms have structure. Real, physical, predictable structure. Now here's the part where I want to mess with your sense of scale one more time. You know how I said a grain of sand has about 10 quintillion atoms? Let's put that in perspective. If you took all the atoms in a single grain of sand and spread them out in a line, one atom thick, how far would that line stretch? Roughly from here to the moon. And back. Twice. That's how small atoms are. And yet we can measure them. We can count them. We can move them. We can predict their behavior with insane precision. That's not magic. That's just what happens when you take reality seriously and refuse to settle for vague answers. But here's the thing I really want you to understand. The reason we know atoms exist isn't because of one experiment. It's because of 10,000 experiments. Brownian motion is one line of evidence. Diffusion is another. Crystal structure is another. Spectroscopy is another. Chemical reactions, radioactive decay, mass spectrometry, X-ray diffraction, nuclear magnetic resonance, electron microscopy, scanning tunneling microscopy. Every single one of these techniques independently confirms that matter is made of discrete particles with specific properties, and they all agree. They all point to the same conclusion. They all give consistent, compatible results. That's not coincidence. That's not luck. That's called converging evidence. And it's the most powerful form of proof in science. When 100 different methods, using completely different principles, all tell you the same thing, you listen. Because the odds that they're all wrong in exactly the same way? Astronomical. So yeah, atoms exist, not as a theory, not as a model, not as a useful fiction, as a fact. A fact so well established, so thoroughly tested, so dearly tested, so deeply integrated into every corner of science and technology, that denying it is like denying the ground beneath your feet. And here's the kicker. This whole conversation, this entire video is happening because of atoms. The light hitting your screen. Photons exciting electrons in pixels. The electricity powering your device. Electrons flowing through conductors. The signal carrying this information. Electromagnetic waves interacting with atoms in transistors. Your eyes detecting the image. Photons hitting rhodopsin molecules in your retina. Your brain processing the information. Neurons firing. Neurotransmitters crossing synapses. Sodium and potassium ions flowing through channels. Atoms, all the way down. You're not watching a video about atoms. You're watching atoms perform a video. Every photon, every electron, every molecule in your body right now is doing exactly what atomic physics says it should do. And the fact that you can understand this, that, you can think about it, question it, test it, is itself a result of atomic scale processes in your brain. That's the reality you live in, not the smooth, continuous, abstract world of philosophy. The grainy, discrete quantum world of actual physics. And once you see that, really internalize it, everything changes. You stop asking, do atoms exist? And you start asking, what else can we do with them?